Question 25. The structural formula of an ester methyl methacrylate is shown. Write a balanced equation using structural formula for the production of methyl methacrylate from methacrylic acid. Now, this is an ester. And the way we know that is because we see a carbon-oxygen double bond with a same carbon single bonded to another oxygen. The reason I've included this question in here is to help you adapt to different questions and not worry about things that look unnecessarily complex, but they don't actually do anything for you. So this double bond here means absolutely nothing to us. Do not let it confuse you, okay? So as far as we're concerned, in terms of figuring out the alcohol and the acid that got used to make it, identify where the functional group is, and then just worry about the carbon chain. I don't care about what the carbon chain actually looks like. Draw it out exactly, and then just fill in the functional groups back in. Yeah, so don't let the unnecessarily complex looking structure confuse you. So they're not asking you to just draw the alcohol and the acid, they're asking you to draw the entire equation. So which is alcohol plus acid turns into ester plus water. So I'm going to rewrite the same thing. And then when I get to one section, I know that when I go back to the acid, I have the double bond O, I have the single bond O, and then I just put the hydrogen back in to make it a carboxyl functional group. That's all I'm doing. And then on the other side, with a single bond O, I just put in an extra hydrogen to make it an OH. Yeah? So identify the ester functional group. Don't worry about the carbon chain. It looks unnecessarily confusing just for the sake of it. Esterification, don't forget it's a double arrow. And then what's the catalyst that I write above my double arrow?
H2SO4. Wait.
Yes, what kind? I'll give you
Dilute.
water gets made, water gets removed. I need a dehydrating agent.
Oh, concentrated.
Yes.
Wait, no. Yeah.
Concentrated H2SO4. And then ester plus water, they've given me the ester, so I kind of just copy paste my drawing. H3C, C, H2C plus a HOH. Okay. Any questions?
No.
Okay, so key lesson here, we're exposing you to a bunch of different questions. Don't let any unnecessary information confuse you. Okay. Question 26, justify the process of purifying a sample of ethyl ethanoate produced after an esterification reaction after reflux. So this is not about the experiment itself. This is not about the reflux. This is about the process of purifying it after you've done the reflux. So we've talked about the reasons for reflux, the reasons for a heating mantle, the reasons for like those boiling chips before. So go back to look at the lesson recording if you need to. This is about the reasons for the purification afterwards.
Right.
And it says justify, which means give reasons. So, well, tell me, what do you remember about the purification process? We'll go from there.
Oh, I don't really remember much from this. Oops.
Yeah, that's all good. So there's a separating funnel. You remember that?
Boiling chips?
No, boiling chips is during the actual
Oh, right.
esterification. This is for purifying it after. Now, the main thing you use is a separating funnel, and then you purify it a lot more with distillation afterwards. But right before the separating funnel, there's a step that you do beforehand, and you neutralize any excess. Actually, let's do the statement first and then the justification after. The first thing you do is you mix the reaction mixture with sodium bicarb, which is NaHCO3. This is NaHCO3 is basic, which means it can neutralize any remaining carboxylic acid. But then also you don't just have the carboxylic acid, you also have your H2SO4 catalyst. So it's to neutralize any remaining carboxylic acid as well as H2SO4 in the mixture, just so you don't have to deal with any corrosive stuff. So that's the first thing you do. Number two, once you've done that, then you can move it into the separating funnel. So transfer to separating funnel. And then now that's the mixture is in two layers. There's an organic layer containing the ester and an aqueous layer containing everything else. The two different layers have a different density and they don't mix. That's the reason why you're able to separate it with a separating funnel. So the requirements for using a separating funnel is they don't mix and they have a different density. Now, your aqueous layer is more dense, which means it's going to go down to the bottom. So aqueous layer, more dense. So it will exit the separating funnel and then you'll keep the organic layer inside of the funnel. So that effectively separates the two. And then number three, to purify it even further, you're going to transfer the organic layer to a fractional distillation column. The reason you do that is because I know we said in point 2 that the organic layer only has ester, but you know how we said when we were studying trends in solubility that if the alcohol is a little bit smaller, then the OH is a bit more powerful, so it's a bit more polar, so then it can dissolve in water. But then as the as the carbon chain gets a bit longer, the carbon chain is non-polar, so then the molecule becomes less soluble in water.
Right.
So then it's possible that you have bits and pieces of the alcohol that does dissolve in water, ends up in the aqueous layer, but then isn't that soluble in water, ends up in the organic layer.
Right.
So I know we said it's mostly ester in the organic layer, but you might still get some traces of alcohol, some traces of carboxylic acid in there. So you're going to transfer to the organic layer to boil off trace amounts of carboxylic acid or alcohol in the organic layer. Now, the reason this works is based on what we've talked about with boiling point. Alcohols have an OH, carboxylic acids also have an OH, esters only have a carbon-oxygen bond. So esters can form dipole-dipole forces, but alcohols and acids form hydrogen bonding forces. So alcohols and acids have a slightly higher boiling point. So the ester is going to boil off first. So I'll change this actually. We're not boiling off the alcohol and the acid. We're boiling off the ester.
Right.
To separate it from the trace amounts of acid or alcohol. So the ester has a lower boiling point, which is why it goes off first. Okay, good. 27. Draw a series of equations using structural formulae to show the production of ethyl ethanoate from ethene. So this isn't a flowchart question. This is a flowchart question, but they haven't drawn the flowchart for you. We're just writing the equations ourselves. Now, ethyl ethanoate is the name of the ester. So what's the alcohol and what's the acid you need to make?
Okay, so ethyl. Okay, so the alcohol is ethanol,
Yeah.
and then the acid is ethyl ethanoic acid.
Yeah, ethanoic acid. Good. So you need two reagents to make the ester. You've been given one reagent, ethanol, so we need to start off at you've been given ethene. So we need to know how to get from ethene to ethanol and from ethene to ethanoic acid. Okay, so let's start off with ethene to ethanol first. I have ethene. How can I get to ethanol?
Ethene to ethanol. Um, okay, so we add an H2O, so we
Yeah, good. We will do a hydration reaction. So let's write the equation using structural formulae. This is ethene. I would add HOH. Single arrow. What do I write above my arrow? I need a hydrating agent.
dilute H2SO4.
Yes, dilute H2SO4. And then I will make my ethanol, and that's good. So I've got the alcohol now, it stops there. Now, how do I make the acid though?
Um,
Can I make an acid directly from an alkene?
no.
No. How do you make an acid?
Um, aldehyde,
Yep. Well,
then
then we
it,
don't have an aldehyde. Where does the aldehyde come from?
oh, we have to make it.
From?
Oh, what's that reaction called?
Starting with
Uh,
an O.
oh, oxidation.
Oxidation, good. And you're oxidizing an alcohol. So when you hydrate the ethene, you make the ethanol. You need to save some of that to go make your final ester, but you're going to take some of the ethanol and go make the other acid.
Oh, right,
Yeah.
okay.
So you're going to save some, but then you're going to take some for another reaction. Okay. And then we don't make the acid straight away. We make the aldehyde first. So double bond O. And then what's the oxidizing agent? Which one do you want to use?
Um, oh, what was it? Oh my God, I always forget
So
this.
it can either be
Wait, there's two, right?
yeah, there's two. So you can either do acidified dichromate, Cr2O72 minus, or if you want, you can do acidified permanganate. You don't need to
Oh,
write both, just choose one to go above the arrow.
dichromate is the
And
one.
then same
Right.
thing now just with your carboxylic acid functional group. Okay. This makes the alcohol though, sorry, this makes the acid though, but I want to go to making the actual ester, the ethyl ethanoate. So my third equation is the acid plus alcohol turns into my ester equation. Okay. And when it's the ester equation, what kind of arrow am I going to use?
Double.
Double arrow. What do I have above my arrow?
Um, okay, we are dilute H2SO4. Wait, no.
Concentrated
Concentrate.
H2SO4. And then I make my ester. So my carbon oxygen double bond, single bond, and then a CH2, CH3 on one side. And then the carbon with the functional group already counts as one carbon. So I just need another carbon here.
Right.
And then what else do I have on the right-hand side for an esterification reaction?
Water.
Water. Acid plus alcohol turns into ester plus water.
Right.
Okay, any questions? All right, awesome. Same thing for question 28. They haven't asked you to draw the equations, they just asked you to describe the method, but very similar process. Describe a method of producing ethyl pentanoate from samples of ethene and 1-pentanol. Support your answer with balanced chemical equations using structural formulae. Now, this is a 9-mark question. You would probably benefit from having a go at this, a long response form, send it through for feedback.
Okay.
It's a 9-mark question, so we want to add as much detail as we can about this here, yeah? So when it says describe a method, which means you want to go as far as talking about what reagents you need, including the equations, talking about the color change for the oxidation and things like that. Yeah. So it's a 9 marks. So we want to include as much detail as we can. And it's relatively easier to structure this one because it's a method question and it's not like it is a long response question, but method questions are easier because you just do 1, 2, 3, 4, 5, and you don't have to worry about like paragraphing.
Yeah.
So really, it's just 1, 2, 3, 4, 5, so on and so forth. So you're making ethyl pentanoate and you're making it from ethene and 1-pentanol. So similar to 27, you need to hydrate your alkene to turn it into your alcohol. So we're gonna hydrate ethene with water to produce ethanol. And what catalyst are we going to mention?
Um, Hydrate, so dilute H2SO4.
Dilute H2SO4. And then that's pretty much it for that one. I don't really have to talk about color changes with this one. I don't really have to talk about equipment. I have to talk about equipment a lot when I get to the actual ester part. And then the 1-pentanol, we're going to oxidize 1-pentanol. And then, by the way, leave a line between step 1 and step 2 and write your equation using structural formulae. Oxidize 1-pentanol using, we're going to do acidified dichromate as the oxidizing agent. And then this is a describe question. So we want to add a bit more detail. What color change are we expecting?
Um, Green. Wait, no.
To green, yeah.
Orange to green.
Yeah, orange to green, good. Now, when I oxidize 1-pentanol though, I don't get to pentanoic acid straight away. I get to pentanal first. So I want to make sure I have enough oxidizing agent to eventually turn into the acid. So I'm going to mention using excess acidified dichromate. And then write your equation, alcohol to aldehyde to acid after. That's in this section here. And then number 3, when you mix the acid and the alcohol together is where the bulk of your answer is going to come from because there's a bunch of things you have to mention with making the ester. So what do you have to talk about? What kind of heat source do you use? Bunsen burner?
Um, a heating thing,
Heating,
mantle,
heating mantle. You're going to tell them why? Why won't we use a Bunsen burner?
because we don't want to have organic chemicals around an open flame because it's very
Yes.
flammable.
Yes, good. Organic chemicals are flammable. You don't want to expose to an open flame. What kind of flask do we use?
Conical?
No.
Oh, what is that? It's that wide one, isn't it?
Yeah, it's the round bottom flask. And you use the round bottom flask to promote even heat distribution. What are the little ceramic things you put in the flask?
Boiling chips?
Boiling chips. And that's to evenly distribute the heat as well and to prevent flash boiling
Yep.
or superheating. Okay, heating mantle, round bottom flask, boiling chips. There's reflux, but there was one more.
Um, the anaerobic condition things? Wait, no, that is for something
No,
else.
that was for fermentation.
Um,
Oh, the concentrated H2SO4.
right.
So concentrated H2SO4 catalyst. And then lastly is the reflux you want to talk about the most. So why reflux again? Do you remember?
So that oh no, I'm forgetting.
Okay. So organic chemicals are volatile, which means they turn into gases easily. Organic chemicals are volatile, which means you want to condense it so it does not escape into the atmosphere. Also, the reason why you condense it back down and you don't just have a lid so that it stays as a gas inside of the container is because you want to prevent overpressurization. Gases exert a lot more pressure than liquids do. So you want to condense it down into a liquid so that it doesn't escape, but also so it doesn't create too much pressure inside of the vessel. So this is for making the ester. But then it's a 9-mark question. You can also talk about purifying it afterwards as well. So the things we talked about before, about sodium bicarb, about the separating funnel, about fractional distillation, you can talk about it down here as well.
Right.
So include your chemical equations, include the equipment, include the method, color changes, anything you expect. Enough to get your 9 marks. This one's easier to structure because it's just 1, 2, 3, 4, 5.
Right.
Okay. Any questions?
No.
All right. Okay. Question 29. Complete the following flowchart by drawing the structural formula of the unknown compound QRSNT. You start off with 1-butene and you're adding H2O. So this is a hydration reaction, and the catalyst this time is phosphoric acid, not sulfuric acid. And then you make 2 chemicals. That's because there's a major product and there's a minor product. So you know how butene looks like this? When you add the
Yeah.
water, you can either put the OH here or you can either put the OH here. Yeah?
Yeah.
So we don't know which one to put where yet, so we have to keep going. Oh. Now, the product on the left, there's no reactions that it keeps on going to. The product on the right goes to react with dichromate, which is an oxidizing agent. What kind of alcohol do you need to oxidize?
A primary or I mean not a primary or secondary.
Primary or secondary? So in this case, it actually works out because if you put the OH here, it's primary. If you put the OH here, it's secondary. So either way, it goes on to the oxidizing agent.
Right.
But here's the thing. After you oxidize it, it turns into butanoic acid.
Mm-hmm.
So what kind of alcohol does it have to be, primary or secondary?
Primary. Wait.
Primary. Good. So compound R has to be a primary or a secondary alcohol for it to oxidize. But then we look further and we realize compound R, after it oxidizes, it goes into butanoic acid, which means it has to be out of primary or secondary. It has to be the primary alcohol.
Right.
Yeah. So compound R is your primary alcohol. And then compound Q is going to be your secondary alcohol. So compound Q is when you put the OH here.
Mm-hmm.
And then compound R is when you put the OH here.
Yeah.
Okay. So, and then compound R oxidizes and then it turns into 2 products, which is possible because we said secondary alcohols, if it oxidizes, it only makes 1 product, which is your ketone. If it's a primary alcohol, what does it go to before it goes to your acid?
An aldehyde.
An aldehyde and then a carboxylic acid. So compound T must be the aldehyde, and then you get the butanoic acid.
Right.
Yeah. And then butanoic acid is an acid, Ethanamine is a base. So this is an acid plus base turns into salt plus water equation. So compound S is your salt.
Mm.
Okay, so this is all of your structures. So in key learning from this question, don't be scared of organic acids and organic bases reacting. They react the same way that an inorganic acid and base from module 6 does. When you mix an acid with an amine, it produces an amide. So this is compound S. The reason it's not specified in your syllabus is because they kind of don't have to. I guess this is sort of one of the trick things that they've done. They've taught you organic acids, they've taught you organic bases, and they haven't taught you organic acid and organic base reactions. They don't have to because they taught you acid base reactions in module 6 previously.
Right.
Yeah. So get rid of the OH, get rid of the H so that it makes the water because acid plus base turns into salt and water. And the thing you have left over, stick them together to make your salt. So compound S is N-ethyl butanamide.
Yeah.
Any questions?
No.
Okay. One more. Question 30. Draw the structural formula in the missing boxes of the flow chart. You start off with compound A and then you add water to it so it turns into ethanol. So this is like the previous question that we did. If you add water to it and it turns into ethanol, then it must have started off as ethene.
Yeah.
So double bond carbon. If you can't think of it that way, then you can think of it the other way. Compound A plus water makes an alcohol. So if you get rid of the water from the alcohol, you dehydrate the alcohol, you get an ethene.
Yep.
Now, after that, ethanol, you react it with dichromate, which is an oxidizing agent, and it turns into compound D. So it could either be ethanol or it could either be ethanoic acid. So we have to keep on going. Compound D reacts with compound E with H2SO4. So compound E is probably an alcohol, and they're mixing together to make an ester. So compound D must be the carboxylic acid.
Yeah. So ethanoic acid.
Yep. So 2 carbons again, but change the functional group. And this is going to be ethanoic acid. Then it stops there for now because I don't have E just yet. Compound C, I add a HCl to it and it turns into our 1-chloropropane.
Right.
Now, they don't tell me that there's UV light. It could, actually, no, it wouldn't be a substitution reaction. If it was a substitution reaction with the propane, then I would need chlorine, not hydrogen chloride. So this is an addition reaction again. I would have started off with propene.
Right.
And it looks like this. Now, 1-chloropropane is actually the minor product. If you look at this, you would, according to Markovnikov rule, you'd actually put the chlorine on the second carbon, not on the first. So this is actually the minor product, but anyway. And then 1-chloropropane, you now mix it with NaOH. Anytime you see a halogen with a OH, whether or not it's from water, whether it's from NaOH or KOH, it is a substitution reaction.
Right.
So I get rid of the chlorine and I replace it with an OH. So originally it would have been this. Now I just get rid of the chlorine and I put an OH there instead.
Right.
So I've got compound E now. Compound E is propanol. Compound D is ethanoic acid. The first part of the ester name comes from the alcohol. The second part comes from the acid. So if it's propanol, then it's propyl. And if it's ethanoic acid, then it's ethanoate. So it's propyl ethanoate. draw in my carbon-oxygen double bond single bond for my ester functional group. The alcohol section, the propyl, gets the single bond oxygen, so CH2, CH2, CH3. And then my acid part of the name, the second part, gets the double bond oxygen. So I put in an extra CH3 to get 2 carbons for F.
Right.
Okay. Any questions so far? All right. Now this final one, this is actually outside the scope of this course. We don't do haloalkane and ammonia reactions, but I'll let you know this is part of, I think it might be in our flow chart. Let's go to our flow chart. This isn't part of the syllabus, but it's might be part of the flow chart. You have, yeah, here you go. You have an alkyl halide. If you react it with ammonia, then it turns into an amine. So this is outside of the scope of the course, but for the sake of completing this, so 1-chloropropane looks like this. Cl goes here. And then all that happens is if it becomes an amine has an NH2 functional group. So all that happens is instead of the chlorine, you now have an NH2. So this would be 1-propanamine.
Yep.
Okay, good. Question 31. Draw the structure of the polymer polyacrylic acid showing 3 repeating units of its monomer given below. Now, I know there's a COOH. This is not a condensation polymer though, because for a condensation polymer, you need 2 functional groups. You need a carboxyl with an amine, so let's go condensation polymer. You need a carboxyl with an amine, or you need a carboxyl with an alcohol, with a hydroxyl. You just have a carboxyl. This is just something that's bonded. This doesn't make a condensation polymer. What you're actually concerned with here is this double bond. So this is actually an addition polymer question.
Right.
So same technique we'll do always. With addition polymers, you tend to stick it up and down. It's easier to look at. So I'm just going to redraw this quickly and put my things up the top and bottom. And then when you're going monomer to polymer, you get rid of the double bond because the monomer double bond breaks apart so that they can all string in a line. So when I go monomer to polymer, I'll get rid of this second line in the middle. So this is my repeating unit, and all I do is draw it. They've asked me to draw it 3 times. So
Right.
H, H, C, C. Now, if they didn't tell me how many times to repeat it, I draw extra lines at the end with square brackets, and I do subscript n being however many times to repeat it. But because they've told me to repeat it 3 times, I assume that my molecule ends here. So these carbons at the end, I'm just going to fill with extra hydrogens.
Yep.
Okay, any questions?
No.
All right. Question 32, draw the 2 monomers that synthesize to produce the polymer called Kevlar given below. Now, the fact that they've even asked me for 2 monomers, even if I didn't look at the structure, I'd know it's a condensation polymer because addition monomers, there's only one type. So when it's addition polymers, draw the lines between every 2 carbons. That's all you need. For condensation polymers, you draw the lines between the functional groups. So this is 1 because I have the NH functional group, and then this is the other because I have the CO functional group.
Right.
Now, because it's a nitrogen and not an oxygen, I can see that this is an amide link. So when I go back to draw the monomers and refill my functional groups, I'm going to make a carboxyl functional group and I'm going to make an amine functional group. So let's draw the hexagon back in first, and then I'll have the C double bond O, C double bond O. that makes the carboxylic acid. So when I draw that back in, I'll just add an extra OH.
Mm-hmm.
And then for the other one, I know that it makes an amine. And then an amine is normally NH2. So I've already got one hydrogen. I just put the extra hydrogen in. So these are my two monomers.
Right. Yeah.
Okay, any questions? 33, draw the two monomers required to produce the polymer polyethylene terephthalate below. Once again, the fact that they've told me two monomers implies that it's condensation. So I'm going to split it at the functional group. This time it's C single bond O, not C single bond N. If it was C single bond N, I know it's a carboxyl with an amine. Because it's C single bond O, it's an ester link. It's carboxyl hydroxyl.
Right.
So I split the line about here.
Mm-hmm.
So this is one, and then this random chunk is the other one.
Right. Okay.
So I'll draw in my hexagon again. The double bond O I know makes an acid, so I'll just put in my OH when I go to draw the monomer again. And then for this section with the single bond O, we said that it's an alcohol. So I'm going to draw that back in first, and then I'll worry about putting the functional group in after. H, O, O, and then where the O is, I'll put an extra H there to get the hydroxyl functional group back in.
Okay.
All right. And then question 34. Draw the polymer produced by the monomers below. The monomers, once again, two monomers means condensation polymer, not addition. And I see OH on either end, and I see carboxyl on either end. So I'm making an ester link.
Mm-hmm.
So I want to not get my carbon chains wrong. So I'm going to draw my carbon chains first. C, 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 6 carbons for the acid. And then with condensation polymers, I know that our water gets condensed, which means I have to get rid of an OH and a hydrogen. And then I just make the ester link, which looks like this. So O on either side. And then once I've got that, I don't put the OH from the acid. Notice how I went C double bond O with a single bond O, but I don't have the H. I'm just going to go O, and then I'll do the carbon chain for the other monomer, this CC here.
Okay. Right.
Okay. Now, I can keep on going. They haven't told me how many times they want it to repeat, so I'm going to do this in a summary way. So let's end my carbon chain here. O. And then I'm going to do my lines out. And then I'm going to do square brackets N. They haven't told me how many times they want it to repeat, so I'm going to do it the summary way. Otherwise, it's going to keep on going forever. Fill in my hydrogens. So you can see the ester link in the middle. Notice how on the left-hand side, I didn't make the ester link. It's because on the right-hand side, I have this single oxygen here. So it's assumed that as it keeps on going, that you have an oxygen on this side that would continue the ester link.
Right.
So that's why I didn't draw an oxygen on the left. It's because I put it on the right-hand side. So technically they should connect if it was to keep on going with each other.
Right.